Hello, in this video I'm going to talk you through some of the common things you'll find in an OOMMF MIF problem file. So on the left here I've got the example file I've been using before in my other videos, xspring.mif. So the first thing we come to are these set pi and set mu naught lines, and so the MIF format uses essentially TCL or Tickle programming language. In fact, if you've got any experience using that language, then you'll probably find it easier to follow and use MIF files, because they, like I say, they do essentially use that language. What these two lines do is set constants for use later on in the problem file. So we've got set pi, which is the result of the expression for atan 1.0, and then mu naught is then the expression which is 4 times the value of pi, which is denoted by the by a dollar sign followed by pi. So it's 4 times the value of this variable pi times 10 to the minus 7. These two lines, they're commonly found in a lot of MIF files because they're useful things to have initially. So the next sort of block we come to, this specify block, is what defines the extent of our simulation region, and OOMMF calls these things atlases, and there are different types of those that you can use. And like I say, for full details you should really check out the OOMMF users guide, which will give you more information about it. But I'll just talk you through what's going on in xspring.mif, and this is setting up two different regions within or different regions or atlases within a multi-atlas environment, which encompasses the two of them. And so the first atlas here is given the name top here, and this is a box atlas with an X range, Y range and Z range, and then there's secondly another atlas with the name bottom, which also has an X range, Y range and a Z range, and these are both combined together into this multi-atlas environment, which specifies the full simulation region. Now the next section in the MIF file, this specify OXS underscore rectangular mesh, this is what defines or specifies the discretization of the simulation mesh or the simulation region into a mesh, and we can see here it's fairly straightforward, where it just specifies a cell size. Here is 10 nanometers by 10 nanometers by 7 nanometers, and it's connected to this atlas with the name of atlas, which is defined there. So next, having set up the simulation region and how we're going to, or the cell size that we're going to simulate it with, this MIF file xspring.mif then specifies the exchange interaction, and there are various ways that you can represent the exchange interaction in OOMMF, and again I recommend you check out the user's guide for full information, but in this case there are 3 different values of the exchange strength denoted by A. So in the first case there's the value inside the top layer, then there's the value inside the bottom layer, and then there's also another one that specifies the interaction at the interface of the layers. So there are 3 different exchange interaction strengths going on there. Next, there is a specify block which defines a uniaxial anisotropy, and here it uses something called an OXS atlas scalar field, which allows you to set different values, different scalar values, depending on the atlas. So at the beginning of the MIF file, 2 different atlases were defined, one as the top and one as the bottom, and what this does is set the K1 value for the uniaxial anisotropy as 0 in the top layer and 520 times 10 to the minus 3 in the bottom layer, and then it also says that the axis of the uniaxial anisotropy is along 1, 0, 0, so the x direction. Now the next block, this is a very useful one. This is what specifies the Zeeman energy, it looks like there's quite a lot going on, but essentially it's quite straightforward. First of all, there's a multiplier at the beginning, which allows us to specify the units that we're going to input the field. And in this case, this expression of 0.001 divided by mu naught, that means that our field units are in millitesla, although you could set that essentially to whatever you wanted. And then there's also this H range section, and it's here that we specify the range of fields that we want to apply in our simulation. And this is set by, on the left-hand side, there's 3 numbers for the initial field condition, so Hx, Hy, and Hz is in the initial condition, and then there are 3 numbers for the final magnetic field situation, which is so here 500, 50, and 0, and then finally there's a number for the number of steps that are going to go between the 2 different field situations. So then on the second line it goes from 500, 50, 0 to minus 500, minus 50, 0 in 20 steps, and then finally it goes minus 500, minus 50, 0 to 500, 50, 0 again in 20 steps. This next block, the specify OXS demag, that's a very simple one. We don't have to pass any arguments to that, but all this does is say to OOMMF that we want it to calculate the demagnetization energy. So we just want to leave that line in there just to turn on that. Next is a rather important aspect of OOMMF, which is the evolver, and it's the evolver that updates the magnetization configuration from one step to the next. And again, check out the OOMMF users guide for full details. And finally, we get to this specify OXS underscore time driver, and it's the time driver that really coordinates the action of the evolver in the simulation. And most importantly, really, from our point of view, is that it also sets the stopping condition for the simulation. In this case, it says when the rate of change of magnetization is less than this value 1, then consider the simulation finished. And it's also here that we set the initial magnetization configuration. So that's it. There can be a steep learning curve with OOMMF and MIFF problem files, but I think if you look or take your time going through something like the exchange spring example or other examples, and think about the different terms or different aspects of magnetization that you're wanting to simulate, if you work through that and then have a read of the OOMMF user's guide to get a better understanding for what's going on, then it's not too bad eventually if you just copy and paste from the different examples. Thanks for listening.